And hello YouTube, welcome back to our Turbulence modeling video series. So today I want to talk about the OpenFOAM practice case, so to speak, and this is a just good example for you guys to follow, to take a look at if you are interested to set up your own DNS case or LES or RENS case, because I'm going to run all three as far as possible. So again, we found, I'm telling you that the upper limit of a standard laptop is about 4 to 5 million cells. Okay, so what we have here is about 3.9 million cells, and that's about the best we can manage. Okay, this is a DNS size mesh for a Reynolds number of 2350. This is the rough number to expect. Okay, so for LES type, we want a mesh where we have 157 cells in the Y direction, 40 in the X and Z direction. How do I come up with this number? Actually, if we take a look at, we want an X plus of about 8.4. I actually want to decrease it by about 4 times. Okay, so I take this times 4, I will get a delta X plus of about 32 or about 33. That's about the size of the LES mesh. Because LES, large eddy simulation, delta X plus and delta Z plus are about 40 and 20 respectively. So I will just reduce the number of cells in both these directions by 4 times. So you got 157 times 40 times 40. If you divide by 10, it will be a little bit coarse, but yeah, it's just for your knowledge. Yeah. So in general LES meshing, if you want to do a LES mesh, it should be like so. And if you want to split it into 2 domains, then you take 158, which I kind of round up, and divide it by 2. So each half will have 79 cells. For RENS type, that's the easiest actually. You take whatever LES mesh you have, you divide it by 10, okay, and you get this RENS mesh. Okay, I kind of left the cell in the Y direction, so to speak. The Y direction cell. In the Y direction, I kind of just left it hanging, so to speak, so that yeah, I mean, if you have finer cells, it's still quite okay. If you have a near wall model that can handle, the rigorous the boundary calculations, or else technically speaking, the first cell off the wall should be placed in Y plus more than 30. So there needs to be some so-called change, and you don't need a mesh this fine, but I kind of just left it as that. I'm just saying that if you take these two and you divide it by 10, you get roughly a RENS type. Okay, but I just ran this calculation first. I ran this calculation first using K omega SST model. Okay, K omega SST model, and I find that now if I want to change the velocity, I need to go by proportion and change it by the ratio of the Reynolds numbers, and I get 0.22618 meters a second. And if I do a wall shear stress, when I did this wall shear stress, so okay, this is using the Reynolds number of 2350, and that's the results you're looking at now. Okay, the wall shear stress on this right side of wall. Okay, wall shear stress on the wall on the right side. As you can see, it hovers around. It will hover around 2.7. Okay, so you can see it's about 2.77, 2.8. Give and take. It will oscillate. So the last value was about 2.68, which was after a lot of flow through times. So there seems to be some oscillation in time, but that's kind of to be expected, I guess. It's not fully steady state. This is an unsteady Reynolds average Navier-Stokes, so to speak. Okay, but technically speaking, it should reach about steady state. So you can see that the values actually hover between 2.86 and then 2.68. So I'll just give 2.7 as 0.27 as sort of the wash your stress representation. So the friction velocity, give or take, it's about 0.16277. Okay, 0.16277. And this is the Kolmogorov scale based on the new Reynolds number, the reduced Reynolds number, and if you still want to compare it to the bachelor and the bachelor scales, then we need to take a look at this numbers. So because we have a natural convection, we also need to take a look if the natural convection scales are smaller. So that's just a quick check. Our bachelor scales are actually this much, 0.013357.6. Because the Grashof number didn't change, so there's so-called nothing to be concerned about too much. Okay. Alright, so this is just taking purely if the case was the natural convection, because the Nusselt number might change according to forced convection. This one is kind of thinking, you know, if it's a natural convection, how will it be? So anyhow, this is the bachelor scales, which is 0.0133. That's the ratio between the small bachelor scales and the characteristic length of the system. I times the square root number, and the Kolmogorov scale is pretty big. So you can see that the Reynolds number is actually about 10 times smaller than even the bachelor scales in natural convection. So always just use in this case, use the Reynolds number to kind of gauge where your scales should be. Okay, so forced convection. Okay, forced convection Kolmogorov scale will be used as the reference, and that's about 44 microns. So it's a bit bigger this time. And if we were to put this into the equation to see what this length scale here, 44 microns, actually corresponds to in terms of Y plus units. Okay, so in Y plus units, the Kolmogorov scale is, when you substitute everything in, you get about 0.5. So about 0.5 is pretty decent. Not too much change from the last time. It is still very, very much acceptable. And okay, so anyhow, if we use this Kolmogorov scales, alright, we use this Kolmogorov scales, this is actually about 0.52 times the Y plus. And what is the Kolmogorov scale here? And how many cells do we need? Okay, the number of cells we need is actually 1 divided, okay, eta divided by L equals 2. Okay, 1 over 2350 to the power 0.75. Okay, and this is the Kolmogorov scale. So if you want the number of cells, you just take the inversion of this, and you will get about 337.52. This is how many cells you want if it's a Kolmogorov scale. But actually, you don't need that many cells. You can actually just divide this number by 2, because by default the Kolmogorov scale is already half the Y plus. So divide by 2, and we need about 169 cells, okay, in each direction. So it's not quite 157, but okay, if we take 169 and we cube it, that is approximately 4.8 million cells. This is still more manageable than what we have initially, but this is really the upper cap. You can't go any much more than this, okay, in terms of mesh refinement. So don't do any more. That's enough. So what we have is we will try to have this, like, okay, if this is the center and this is the wall, okay, so one Kolmogorov scale is enough for near the wall, and I'll use 2 Kolmogorov scales. far away from the wall. Okay, 2 Komogoro scales far away from the wall. That's within the quasi DNS guidelines that we see in literature. So this is still perfectly fine. If we want to coarsen the mesh a bit, that should still be okay. Okay, so right. And actually I ran just the test simulation just to see where we are with things. Okay, even if you use the 157, so-called 157 kind of a mesh, where would we stand? Okay, I did a IDDES, okay, which is what I'm doing now. After I did my RANS calculations, I mapped the results to a IDDES. I'll show you how maybe next time. But okay, I show you what's the mesh like. So this is the RANS case, which is finished. So IDDES case I'm running. So this is what I'm running now. This is actually what I'm running now. And the CPU is C4 processors of buoyant pimple foam, and it's been running for the last few videos. So yeah, let's see. Not buoyant pimple foam. You see how long it's been running. Okay, so DNS will probably take maybe a few weeks to finish in continuous running. This IDDES maybe takes about a few hours or maybe a whole day. Okay, if you look at this mesh refinement, 157 times 16 times 16. Okay. All right. So let me show you the block mesh. So it's been running for, you can see 20,000 seconds, which is somewhere about 1/4 of a day, because one day is about 86,000 seconds thereabout, if my memory serves me well. Okay, so sorry, that's VI system block mesh. Okay, so this is the mesh I'm using. Oh, wrong one. Block mesh dict IDDES. Okay, this is the mesh I'm using. So I divide the X and Z directions into 16, so it's a bit coarser than what I have, and we use 79. We divide the Y into 79 bits. So okay, how much is that? How much can we get away with? All right. Yeah, how much is this actually? If we divide 12 cm into 16 nodes, and we get the IDDES mesh size, we get about 87.86, which is a little bit coarser. In fact, it's a little bit too coarse for IDDES in general. So we need to reduce this maybe by 2 to 3 times, or maybe 2.5 times. So we should actually change if we want to run a true IDDES, this should be about 40, not 16. So I kind of mistyped or something there, but it's interesting. It's a good for mesh refinement study anyhow. If we have slightly coarser than IDDES, let's see how much time we can save. Yeah. So what's the length scale we are talking about if we shift it to 157 cells instead of, you see here, the recommended thing is we have about 169 cells, but that's like 1 million cells more than, let's say, if we use 157 million cells, 157 cube kind of mesh. So even that little bit of a change actually makes a big difference of about 1 million cells. So let's see whether we can, we still want to see whether we can get away with using a 157 cube. Okay, so what we do is you can take a look at the wall shear stress. So CD post processing, and we take average values left 100. Okay, so actually for the first 100 seconds I run a RANS simulation, then I mapped the results over to IDDES and I run it, but next time I'll show you how. Okay, now I just tell you the physics first on the so-called not physics, but just some of the values. Okay, so you can see that the typical values here are about 2.61 times 10 to the minus 1, or 0.26. All right, 0.26. which is slightly lower than this. Okay, so and the other side, this is for opposing mixed convection. If you are doing what do you call it? If you are doing the aiding mixed convection, you'll see this number is about 3. Okay, 3 times 10 to the power of minus 1. Okay, 3 times 10 to 3.05, right? 3.05. So that's about, give or take, this much, right? This much. So actually, if we have a square root of 0.31 divided by 1019, okay, if we do a u tau based on that, okay, we do a u tau based on that, 0.31, that will give you about 0.175. Okay, 175. Okay, and let's see delta x or delta y plus, and we 157 or 158 cells mesh size. Okay, so this is using 158 cells instead of 169. You just heuristic I calculated earlier. So that's actually 0.015 meters divided by 158. Then I multiply by this velocity here, and I divide by 1.44 times 10 to the minus 6. Let's see whether this actually fits, like maybe 1 or less. Okay, so when you chug in the numbers, you'll get an average cell size of 1.154. Y plus equals to 1.154. Okay, so remember your smallest cell size is actually half of this. All right, this is actually half of this, right? Let's see. Smallest equals to 1.154 divided by 2. Okay, what's this divided by 2, and you get 0.57668. all right, this is roughly what you will get. Now this is very important because it says that, you know, your smallest y plus size actually fits very well with what the criteria is for DNS. For DNS, criteria is delta y plus, the smallest is about 0.8. Okay, so if you have it slightly smaller than that, absolutely good. And your largest cell size will be 4.5, y plus 4.5. And I mean, you just take a quick math calculation, you get this, you multiply by 2, that would actually just give you about 2.3, right? 2.3, and it's smaller than 4.5. all right, this is smaller than 4.5, so you're within a very safe range. And if you want a delta, you want to look at your delta z plus and everything. Okay, delta z plus. All right, let's see. If you were to take this size in x direction, okay, so delta x plus or rather delta z plus, that's more interesting to see. Okay, hold on. Okay, so this is actually, if you just punch in the numbers, that will give you about 9.171. okay, so this is actually pretty okay. Maybe you just make it a 160, you will actually hit below. No, maybe not 160. Okay, maybe, yeah, I thought if it hits 160, you will actually drop below 9. Doesn't seem like it. Okay, so anyway, your recommended size in the streamwise, which in my case is delta z plus. Some people use delta x plus, whatever. So yeah, because okay, yeah, I think I missed name. This should be streamwise. just to avoid confusion, this is span wise. Okay, so I should say that here I'm talking about streamwise. Okay, streamwise. Okay, streamwise delta z plus stream equals to 0.09. So this is pretty close to where we are. I'm okay with that actually. Okay, it's very little difference. So again, same for delta x. Plus, if I change this to 4.5, 0.45, or 0.045, okay, if this is 0.045, this is the span-wise direction. So actually, if we do this, this will actually just result in this thing being about 3.308 or 038. Yeah, so actually this is actually pretty safe. This is actually pretty safe. We can actually have some leeway to reduce the cell count. This one, it's just about at the limit. So actually we can reduce this a little bit more, and that will be completely okay. But this just goes to show that having a cell size about 159, that actually can do pretty well and serve us well when it comes to doing DNS calculation. Alright, so we don't have to go for the very, very strict 169 cells, 169 cube all the time. Where is it? Yeah, 169 cube all the time. We don't have to go for that. So actually 157 is just about right. Okay, or 159, sorry. 159 is just about right. We can live with that. Okay, so that's what I have for you today. I'll just stop. So next time we can talk more about results and well, the difference between maybe both IDDES meshes when this thing finishes, and of course we try and do it for DNS as well. Okay, and actually, okay, yeah, I'll talk about the DNS meshing next time, and you can see it actually takes up a lot of memory. You can see here it's about 88% of my memory it's being used up. So you can see even for block mesh, it's pretty challenging to generate the mesh. But that's just to pique your interest with this kind of cell size. But talked enough for now. Thanks for watching. I'll see you guys next time. Bye bye.